welcome you all again. Let's get started with the turbulent boundary layers that we are looking into, right? So in the last class we looked at that there is a need for an inner turbulent boundary layer because there was no way of saving the viscous term in the outer boundary layer, right? So the outer layer, other terms were dominant, the turbulent terms and some inertial terms were dominant. So we need to, therefore there was a need for an inner turbulent boundary layer, and then we introduce two new scales, inner scales, that is eta w and uw. We still don't know the nature of them, but we just said that let this eta w should be so tiny, right? So this eta w should be smaller than delta by an order of magnitude, which is at least an order of magnitude smaller than L, okay? And therefore the ratio of eta w by L was very small, okay, is very small, and this value depends on the Reynolds number, okay? So this eta w by value is very small and the value depends on your RE delta, okay? So L, eta w are all functions of x, and as you move along x direction the RE delta is changing, your boundary layer thickness is changing, and therefore the ratio depends primarily on the Reynolds numbers that you are working with, okay? So with this eta w by L being small, some of the terms in the u momentum equation were of second order importance. So to first order, what did we learn? So the u momentum equation, right, we had this u equation. To first order, what this equation reduced to? Essentially 0 to first order I am writing. So we have the first term which is dou by dou y of your u prime v prime over bar, the turbulent term, and one of the viscous term, the viscous shear stresses, which is mu dou square u bar by dou y square. The largest viscous term is balancing the largest viscous term balances the largest turbulence term, to first order, where in the inner layer, right, inner turbulent boundary layer. In this layer these two terms are dominant to first order, and when we introduce the scales, this led to essentially we get our u w, eta w by nu was of the order of magnitude 1, right, and this is nothing but RE eta w 1 inside the inner turbulent boundary layer. This is what we learnt yesterday. So let us call this equation 1 here, okay, and this equation will be the equation, let us say the inner layer equation. So we can call this inner layer equation here. Inner layer equation. So now we have an equation for the inner turbulent boundary layer. Of course the outer one had the turbulent term, the same turbulent term, but we had on the left hand side u bar by dou x, right? Those two were balancing each other in the outer turbulent boundary layer, okay. So now another thing we can see here, we can easily see here is that the eta W takes a form based on the viscosity here. So now I have a length scale eta W, which is the near wall length scale or an inner scale, which depends on the viscosity, right. So I have eta W is nothing but nu by UW. Of course, the nature of UW is required, because in a given flow the kinematic viscosity is known. If you know what is UW, you can find out the eta W, the inner length scale, that is useful to you. We will see what that happens to. So for that to be determined, we will take this equation 1 and then integrate this within the turbulent boundary layer, but within the layer. We are not going all the way to the outer flow, within the layer. So consider equation 1. Okay, so I have 0. This is approximately equal to, because there are other second order terms, and I already told you this equation 1 resulted because eta W by L is small. But if eta W by L becomes 0, then this equation 1 becomes exact. That means it will become 0 is equal to this. Now I cannot integrate equation 1 because still there are second order terms. So I would like to consider in the limit Re delta tends to infinity, what would happen then? In the limit Re delta tends to infinity, eta W by L will become 0. It is small now and it depends on Re delta. When the scale separation becomes so large, in the limit Re delta tends to infinity, eta W by L becomes 0. Okay. So we will consider this. Consider equation 1. If Re delta tends to infinity, then eta W by L will be 0, not small. Okay. Then your equation 1 will become 0 equal to, okay, now you see this is becoming equal to instead of the approximate. So the second order terms are all gone now. So in this theoretical consideration, Re delta tending to infinity, only these two terms are surviving inside the inner turbulent boundary layer. So 0 equal to, I have, if I now integrate this, I get, I'll integrate this from y equal to 0 from wall to some distance y, but this y has to be within your turbulent boundary layer. You should not go all the way where your free stream velocity, you are approaching the free stream velocity. Okay, so it should be y within the boundary layer. So then, so this is only a theoretical consideration. In reality, we never approach this equation, what we are going to. We simply want to integrate it to see what happens. I will show you the data. In the data, of course, this eta W by L is not 0. That means all the other terms, the left hand side, the two inertial terms as well as the viscous and other turbulent terms, all exist in actual flows where you are working with finite Reynolds numbers. See, this is only when in the limit, okay, in the limit Re delta tending to infinity. Alright, so I have this equation now, 0 equal to this, and then if I integrate dou by dou y of minus v prime plus y equal to 0 to y, I have nu dou square u bar by dou y square. So here y should be within the, integration is within the boundary layer. So here y within the turbulent boundary layer. That's because if you have, for example, if you recall this sketch that I had, have a wall and then a boundary layer like this. So this is the interface of your what we call a turbulent non-turbulent interface. Okay, I have not introduced this term so far. So this we call a turbulent and a non-turbulent interface. So this zone is turbulent and this zone is non-turbulent, and then there is an a thin interface here between the two zones. So in the non-turbulent zone, that is where you have your free stream zone. Inside you have a turbulent boundary layer, right? So there is a discontinuity at this position. As I told you, turbulent flows are characterized by three-dimensional vorticity fluctuation. So after this interface, it suddenly vanishes. The three-dimensional vorticity fluctuation vanishes above this interface and below it survives. So there is a sudden discontinuity here, and therefore we don't integrate all the way. This is your y direction, right? So we therefore y within the turbulent boundary layer is what I wanted to say. Integration is not all the way where y is approaching the free stream within, and anyway I am interested only in the inner layer here. So I don't want to go all the way up here, right? So my inner layer is somewhere here. And the inner layer equations are valid also in the inner layer, right? They are obviously not valid outside because the inertial term becomes important, viscous term becomes 0 above. Okay, so you should know that this is only a theoretical consideration here, that is in the limit Re delta tending to infinity, this happens. Okay, so if I integrate, I get, now this is a definite integral, so no constants of integration appear. Y equal to 0, which is the wall here, right? This is y equal to 0, the wall to some distance. So I get easily 0 equal to minus u prime v prime average at some distance y within the inner turbulent boundary layer. Okay, and then I get this minus of the same u prime v prime. This is evaluated at y equal to 0. This is function of y, the first term, second one evaluated at 0, and then I have plus this particular term which is nu dou u bar by dou y at some distance y from the wall, okay, minus of nu dou u bar by dou y at y equal to 0. All terms survive here, or any terms to be removed, because we are applying boundary condition here for, yes, this particular term at y equal to 0, due to no slip and kinematic boundary condition, your shear stress, turbulent shear stress must vanish. Okay, so this term must vanish due to your no slip boundary condition. Okay, fine. So now this means I have, and what is the, is there a name for any of this term that you recognize from your fluid mechanics? This particular term, last term, when you evaluate this gradient at the wall, what is this? Wall shear stress, right? You already know that this particular term is nothing but tau w by rho here, your wall shear stress, right? It is wall shear stress. Okay, so therefore I have now a formula for wall shear stress, that is tau w by rho is equal to minus u prime v prime average plus nu dou u bar by dou y. This particular equation of course is valid in the inner layer, right, and it is also valid in the limit. So if I now this equation is valid only in the inner turbulent boundary layer. and and in the limit Re delta tending to infinity. So for a finite Reynolds number, this will not be equal to, it will be approximate. So wall shear stress is approximately equal to this. Okay, and this is what we call a total stress here. Total stress, because this is a combination of your turbulent shear stress, and this is your viscous shear stress. So the combined total stress is what we are looking into here. Okay, so here integration from some wall, you can take a note here, integrating here from wall to some y distance. Okay, so there is one more thing that we have to consider here. Okay, we have got an equation for total stress, but when we actually plot this data, we see that something peculiar happening here for this particular condition. I am going to show you a graph, then you will see what this looks like. So there is, yes, so now I am showing you data from this same turbulent plane co-ed flow. So I am plotting here this minus u prime v prime, the prime is dropped here. Okay, so basically this is the uv means without the prime I have plotted. So it's minus u prime v prime over bar is your turbulent shear stress, and other one is mu du dy. Capital U is the mean velocity here. So which one is which, you don't know. I have not put the legend here, but I know what it is, or you can also guess. So viscous term, was it dominant as you go away from the wall? This is y coordinate is your wall. Okay, so this is your so y equal to 0 is the wall, absolute wall, and you are going away from the wall when you are going in the x axis. So away from the wall, what terms were important? Turbulent term, and then there was one inertial term. So obviously the viscous term was negligible. So which curve is following that? Yeah, so this dashed line, you see the viscous term is of negligible importance here. So this dashed line is your viscous shear stress, and that becomes maximum on the wall. What about the turbulent term? The turbulent term is dominant. Obviously this term is not balanced by this, that u bar dou x was balancing this straight line, which is the turbulent shear stress minus u prime v prime over bar, and as it approaches the wall, obviously on the wall due to the boundary condition it is 0, and somewhere in between it is balancing each other. Okay, and when you add these two, it is not exactly 1, closer to 1. So if I am looking into the total stress, that is why the equation told in the inner layer I have total stress. So if I am going to add these two, this plus this, it would more or less look like this dotted line here. So this dotted line, which is values coming 1, what is it? Nearly constant, right? In the limit of Re delta tending to infinity, it will be constant because all other terms drop, but for a finite Reynolds number it is nearly constant. So there is something amazing here. Now the total stress is constant. So this layer is also called constant stress layer. So now you may not realize the importance of this. The experimentalists are so happy looking into this graph. Modeling community is also thrilled by looking into this graph. I will tell you why experimentalists are happy. Now I want to know the wall shear stress. Wall shear stress is important for your skin friction coefficient, all this, right, for the drag. Now it is very difficult. Anybody experimentalists here in this class who have done some measurements like this, velocity measurements close to the wall? No, obviously you are turbulence modeling students, okay, not experimentalists. Okay, but ask your friends who have done experiments. It is not possible to measure the velocities so close to the wall to get the du dy accurately. It is extremely complicated. The experimental methods are not easy to get du dy close to the wall. At few micrometers distance from it, you need to get those gradients. That is very difficult, challenging, or next to impossible, you can say. But now they say I don't have to do this. I will measure u prime v prime correlation away from the wall, okay, and that is nothing but my turbulent, that is nothing but my wall shear stress, right? Tau w by rho is sum of these two, but when you are going away from the wall, tau w by rho is nothing but minus u prime v prime over bar, because other term is practically 0. So tau w by rho, the wall shear stress becomes turbulent shear stress away from the wall. So I measure u prime v prime and look at its correlation. It's easy to measure away from the wall, okay, because this they usually use this what is called hot wire anemometry or lasers, PIV equipment. So when you put lasers very close to the wall, you get reflections. So you cannot get data close to the wall, okay. And then if you want to bring this hot wire anemometry, it is having a finite, it's an intrusive technique. So very close to the wall, it gets damaged. So basically very close to the wall, they cannot get data. So this data is obviously coming from my direct numerical simulation, where we can have a mesh very close to the wall and get it, what is the value. So experimentalists are happy. There is a constant stress layer. I measure turbulent shear stress here at a y very far, and I get wall shear stress. They are happy. Now the modeling community is also happy, right? So I don't need to put lot of mesh very close to the wall. For example, let's say I am not really interested in a near wall behavior of the turbulence. Okay, for example, let's say in a turbulent combustion, people don't really worry about what is happening very close to the wall, because walls quench the flame. So if somebody is modeling turbulent combustion, then they are say, I am happy, I already know what should be the wall shear stress, because anyway I am going to compute the turbulent shear stress and I have some idea about what should be. So modeling community is also happy. So this has a very profound influence, this graph, or the idea of this total shear stress or the total stress, right? This is clear? Okay. So we will go back to our graph or the slides here. So this particular total stress or this particular equation is also now, this essentially implies this total stress is constant in the limit tends to infinity, okay, and the total stress or the tau w by rho is approximately constant at finite Re delta, and therefore this particular layer, the inner layer, okay, therefore the inner turbulent boundary layer is also called constant stress layer, okay. So it is almost constant when we work with actual data here. So we have learned that turbulent boundary layer has at least two layers, an outer and an inner layer. Inner layer also has a name called constant stress layer, which is sum of turbulent shear stress and viscous shear stress, okay. So this is what we learned, and so before I go into show you that there are other layers within a turbulent boundary layer, let us go and look at what is this eta w and uw, that we have not finalized, right. So that question we have left it open. So let us go and see what it is.